Hello there, students. Professor Carver here. I want to tell you today about the endocrine system. You already did, but in 2401, look at other human system, skeletal system, muscular system, nervous system. And today we are going to, during this 2402, we are going to see how the human body comprehend. So we are going to see how single cells can interact within our multicellular organism. So let's get started. The endocrine system. So this endocrine system, put in your mind that it's going to interact, it's interacting with the nerve system within our body. So let's see how that's work. So the endocrine system, what is it? This is a system that secretes some molecule messenger that we call hormones. He secretes those molecules directly into the blood, and he can act on distant target cells. And those target cells respond to those hormones for which likely they must have a receptor for it. And the response are, of course, dependent on those specific target cells and this type of receptor that has been stimulated and which kind of hormones has been secreted by this endocrine system. The basic category of hormones, they can be either amino acid based, amino acid, they are the monomer that make a polymer, which is the protein or peptide or polypeptide. They can be either single amino acid or protein, long chain of amino acid, all right? They can be also steroids like lipid molecule derived from cholesterol. As I said, the endocrine cells will secrete those molecules. Those molecules are circulating within the blood, all right, and they target distant cells. Those cells can be either neuronal cells, muscular cells, can be also being endocrine cells. There are different types of receptors that will accept and interact with those hormones. They can be either membrane receptor, that they are only localized on the membrane, and the trigger actually signaling a pathway within the cells. It can be either inside of the cytoplasm. The hormone can diffuse through this plasma membrane, and therefore you got it. It should be a little lipids, because you remember how the membrane is made is a phospholipid bilayers that will not control what's coming in and what's getting out. So the steroid will interact with the cytoplasmic receptor. It can be also nuclear receptors. Those receptors can also be localized on the nuclear envelope. How those hormones are released? They can release either, let me make it bigger, zoom in. They can be either humoral, such as some iron concentration, for example, of calcium, that stimulate this parathyroid gland, secreting parathyroid hormones. They can be also neural, stimulated by nerves. If you can see here, spinal cord, preganglionic fiber, right, receiving a stimulus and stimulating the adrenal gland, which secrete through the blood a catecholamine, which is in this case an hormone. They can be also secreted hormonally. I mean, one hormone stimulates other endocrine gland to stimulate other hormones. As you can see here, the hypothalamus stimulates by secreting a hormone, stimulate the pituitary gland, and the pituitary gland secretes some hormones that will stimulate other endocrine gland, and therefore those endocrine gland will stimulate other hormones. So the endocrine system, they do act as a control system. Where those hormones are made, we are going to look at the gland and the organs. Endocrine gland. Those are purely endocrine gland. Pituitary gland, pineal gland, thyroid gland, parathyroid gland. It doesn't show up here, but if I have the posterior view, we will see it. They are those little tiny yellow stuff that you are seeing here. Let me zoom. Those are the parathyroid gland. They're on the top of the thyroid gland that is look like butterfly. And the adrenal gland, they are like a little hat in the top of the kidney. They are two parts of the adrenal gland, the cortex and the medulla. And of course, we have other organs that they are endocrine, and they are not purely endocrine. That means they can be also other than endocrine, such as the pancreas. Pancreas is a part, we are going to see it when we study the digestive system, is also part of the digestive system. And it have also some cells that they are not endocrine, we call them exocrine gland. We have the thymus gland, the gonad, which is part of the reproductive system, and we have the hypothalamus, which is a part of the nerve system. Let me zoom out. Pituitary gland. Pituitary gland, that's the master gland of the body. And we will see why I call it the master. And the hypothalamus, I'm going to call it the godfather of the body. And I will tell you how these two organs are going to be. One, it's called master gland, and the hypothalamus, which is an accessory gland, is not a purely endocrine because it's a part of the nerve system. It's the godfather of the endocrine system. is localized where the master gland of the body, the pituitary gland, exists. It exists in the sphenoid bone. If you remember when we studied the skeletal body, it produces many hormones that affect other glands. This is why it's the master, because it produces many hormones that affect other glands. So let me go back over here at one of my slides. That's the pituitary gland. Here I show 3 glands that has been stimulated by pituitary gland. Actually, it stimulates more than that. So it is a master gland of the endocrine system because it secretes many hormones that affect other glands. Let me move to this table where I summarize all the hormones that has been stimulated by pituitary gland, or some of them. So we divide this table on the hormone, the target, and the function. Thyroid stimulating hormone, as the word said it targets the thyroid gland. The function, it's stimulating the thyroid hormone, sensitizes, and the release of it, the T3, T4. The growth hormone stimulates so many tissues in our body. As the word said it, the function is the growth. Adenocorticotropin hormones, the target is the adrenal cortex. It releases the cortisol, which is an androgen. The prolactin, the target is the breast, of course, milk productions. FSH, which is a follicle stimulating hormone, of course, it will stimulate the gonads, and it will stimulate the productions of the egg or the sperm. Luteinizing hormone stimulates also target the gonad to stimulate sex hormones. So you see how this is the master gland of the endocrine system, because it stimulates so many hormones, targets so many gland organs and tissues. The pineal gland, and it's the end of the short stalk of the roof of the diencephalon. The cells of the pineal gland, the pinealocytes, site is for cells, pineal for cells that are made within the pineal gland. They have a dense calcium particles, and this is what we can see when we done an X-ray. We saw those dense dark spot there on the X-ray because of the calcium. So far in the nerve system, we talk about the pineal gland and the pituitary gland. Pineal, pituitary. Let me zoom out. The thyroid gland. Thyroid gland exists on the anterior neck, on the trachea, just inferior of the larynx, have a form as a butterfly, produce 2 major hormones. Thyroid hormone, the tyrosine-based hormones, and they have 3 or 4 iodine molecules. We call them T3 or T4, thyroxine. Calcitonin, another hormone, is involved with calcium and the phosphorus metabolism. So those are the major hormones that are produced by the trachea. There are 2 thyroid hormones, tyrosine-based, with 3 or 4 iodine molecules. So we call it T3 with 3 molecules, T4 with 4 molecules. And calcitonin is involved with the calcium and phosphorus metabolism. The parathyroid gland, most people have a 4. As seen here, they have a 4. Those little teeny thing over here. They are embedded on the posterior part of the thyroids. They produce parathyroid hormones, PTH. Next, the adrenal gland. You remember that's the heart in the top of the kidney. We have the adrenal cortex that secretes lipid-based steroid hormones called corticosteroids. Cortico as in cortex. Most important is the aldosterone. It's the main one of the mineral corticoids. And we have the cortisol, which is a part of the glycocorticoid, or hydrocortisone is the main one. So that's are stimulated by the adrenal cortex. They secrete the lipid-based steroid hormones. So in this case, if they are lipid-based steroid hormone, that means the receptor should be either nuclear, it could be nuclear or cytoplasmic, because for the simple reason they can diffuse through the phospholipid bilayer membrane. You get that, right? But if they are simple like polar protein, they can't. For sure, the receptor will be a membrane receptor. Okay, so let's move to the next. Oh, the famous pancreas. Pancreas is also part of our digestive system. We will see it when we study the digestive system. It is a form of exocrine and endocrine cells. The acinar cells, which form most of the pancreas, they are all around the what we call the endocrine cells. The endocrine cells are centralized in the center. We will see it when we see the histology of this pancreas. Those acinar have exocrine function and they secrete digestive enzymes. So this is why the pancreas is a part of the digestive system, because it's mainly made of acinar cells. They are exocrine cells. So we are interested on the islet cells, which are the endocrine cells. So we call it islet cells or islet of Langerhans, referring to the person that discovered them. So this is, let me zoom out a little so we can have the full slide. The endocrine cells, we have 3 endocrine cells in the islet. You see, this is all acinar over his cells. All those blue dots that you are seeing, that are nucleus that has been colored by the methylene, probably blue methylene. You know, this is acinar cells, this is exocrine cells. In the middle, what you are seeing here are the islet of Langerhans or endocrine cells. All right, and you see a lot of capillaries on blood. They are appearing red over here. So we do have 3 endocrine cells. Alpha cells that secrete glucagon. Glucagon rise the blood sugar. Mostly they are peripherally. They are mostly in the periphery. You are going to see them completely in contact with the acinar cells. And we have the beta cells. This is the central part. You are going to see them actually within the center. That are the one that secrete the insulin, that do completely the opposite function than the alpha cells. If the alpha cells secrete glucagon that rise the sugar, the beta cells will secrete the insulin that will lower the blood sugar. And they are more abundant in the endocrine part of the pancreas. And also we have another type of cells, which is delta cells. Those cells secrete somatostatin. Somatostatin as a normal, it's an inhibitor. Anytime any any organ have a sensitivity or gland have a sensitivity to interact with the somatostatin. Somatostatin is going to play a role to block whatever this gland or this cells is secreting. So it inhibits the glycagon, the somatostatin. Les gonad cells, the gonads, tests and ovaries, main source of steroid sex hormone. Again, it's steroidal. That means the receptors on the target cells should be either membrane, not membrane. It could be cytoplasmic or nuclear. Now let's look at the test. The interstitial cells secrete androgens. The primary androgen is the testosterone, the main secondary sex characteristic, and help the function, help promote the sperm formation. Ovaries, androgen secreted by folliculi, directly converted to estrogen by follicular granulosa cells. We will look at those when we study the reproductive system. Granulosa cells also produce progesterone. The corpus luteum also secrete estrogen and progesterone. So those are the tests and ovaries, the main source of steroid hormones. Let's look at now some pathologies. The pituitary. The pituitary, you remember, it secretes growth hormones. If there are too much secretion of growth hormones, that's a lead to a disease or to a pathology that we call jugutism. This is happen if there are so many growth hormones there in the childhood. However, if there are some more growth hormones in the adulthood, we call that the acromegaly. And we show you some pictures. Also, if there are too little of growth hormone and during the childhood, that will create the pituitary dwarfed. If they have too much adenocorticoid hormones, that will create diabetes insipidus. The pancreas will, if they have not enough insulin, they will cause the diabetes mellitus. Thyroid, two pathologies, hyperthyroidism, hypothyroidism. Hyperthyroidism, both of them are an autoimmune, by the way, disease, sorry. Hyperthyroidism, the very common in the grave disease. Hypothyroidism, in the childhood, it will lead to cretinism. Insufficiency of iodine in the diet will create goiter. Adult hypothyroidism, it creates what we call the myxedema. It's also an autoimmune disease. That's a growth factor, growth hormones completely high as a juvenile. This is an adult that will create acromegaly. Pituitary dwarfism, growth hormone not sufficient. Grave disease. That's an hyperthyroidism. Hypothyroidism. Iodine create water or iodine deficiency. Hyper-hypo. Again, some other pathology caused by adrenal gland dysfunctions. Usually, Cushing syndrome caused by ACTH secreting pituitary tumor, rarely by tumor of adrenal cortex. So let's look at first the Cushing syndromes. Too many steroids. And this will create some cancers. Too many steroids. Addison disease, the one that the president JFK suffered from it. It's an hyposecretions of endosecretion of adrenal cortex, usually involve cortisol and aldosterone, low blood glucose and sodium, severe dehydration, fatigue, loss of appetite, and abdominal pain. That's what we call Addison's disease. How we can control the endocrine system? The endocrine system, as any other system, is controlled by a feedback mechanism. The more physiologic feedback is the negative feedback. So this is an axis. If you remember that the pituitary is the master, the hypothalamus is the godfather. So this is the HPA axis. Most feedback that they control the endocrine system go through this axis. Hypothalamic pituitary axis, HPA, all right? The hypothalamus is the most important. It's the one that controls the secretion of hormone, which in their turn control the secretion of hormone by the thyroid gland and adrenal cortex gonad, and this is the way the brain controls those glands. So they are something, I mean, for example, if in our body, I will tell you like T3, T4 has been reduced in our body. Something in our body will sense that, send a stimulus to the hypothalamus. The hypothalamus will release an hormone that we call releasing hormones, right? And they can also do the opposite. We will see it because it will play a role as a feedback negative. So they will stimulate the pituitary, the master gland of the body. So those will stimulate the hormones that will target, like if it's T3 and T4, they will target the specific gland that secrete the T3 and T4, which is the thyroids, and they will release the T3 and T4. And T3 and T4 will continue being secreted until it's reached the physiological level in the body. And then you will go and target the hypothalamus, tell us like, okay, stop secreting T3, stop stimulating the secretion of T3 and T4. I am reaching the level. So in this case, releasing inhibitory hormones will be secreted, which is going to block the pituitary. And this is like a loop. Okay, so this is why we call it a negative feedback. What is negative feedback is the final product control his own production. We will inhibit his own production. The final product inhibit his own production. So this is what is negative feedback. So I talk about it, but it's over here. Thyroid releasing hormone stimulate. I love to see it by pictures. So low level of T3 and T4, right? The hypothalamus will stimulate the thyroid releasing hormone. The thyroid releasing hormone will stimulate the anterior pituitary gland, not the posterior, the anterior, that will release the thyroid stimulating hormone. The thyroid stimulating hormone will stimulate the thyroid follicle to release T3 and T4. Unless it reaches the desired level, the physiological level. As soon as it's released the physiological level, the T3 and T4 will shut off the hypothalamus, and the hypothalamus will, instead of releasing thyroid releasing hormone, he will release thyroid inhibiting hormone that will block the anterior pituitary gland. Or he will shut off, block the secretion of the TSH by the anterior pituitary gland. It's like a loop. This is a negative feedback where the final product is blocking his own production as soon as he reaches his goal. This is why we call it negative feedback. Positive feedback, however, this is very not really common as a physiologic control, but it's happened. You all see it when a lady, she is delivering a baby, we call her to push, and she is pushing. Actually, when she push, when the baby touch the uterine, it will stimulate an hormone that we call oxytocin. And this oxytocin relax the uterine muscle. And more the oxytocin is secreted, more the muscle is relaxed and the baby will come. So the oxytocin stimulates the uterine contractions. So once the baby touches the uterine, he will secrete the oxytocin. The hypothalamus will release the oxytocin, will stimulate the hypothalamus to secrete more oxytocin. More the baby is touching the cervix, more oxytocin is released, more the hypothalamus will secrete more oxytocin. And therefore, the oxytocin will stimulate the uterine contractions by dilating or making the muscle more relaxed of the cervix of the uterine. So the baby can come out very easy. As soon as the baby leaves the birth canals, everything, the lobes stop. So as soon as the baby, I repeat, drop the cervical, touch the cervix, stimulate an oxytocin by the cervix, by the uterine, the hypothalamus sense that will secrete more oxytocin. How? Not by the anterior pituitary, but by the posterior pituitary. It will secrete more oxytocin. And more oxytocin will stimulate the uterine contractions, and this will stop as soon as the baby leaves these canals. Thank you so much. That's end our endocrine system functions and gland and controls. If you have any questions, please email me, and I will reply within the collaborate discussion board or via email. I appreciate your. Thank you.